Welcome back to the deep dive. Today we're strapping on our virtual hard hats and going deep, really deep, into the microscopic world of semiconductor manufacturing. Specifically, we're looking at the design flow of the very features that, power your phone and your server farm. The fight against shrinking geometries is getting absolutely ferocious.
It truly is. It's a high-stakes war fought on the nanoscale. We're talking about feature sizes below the 20 nanometer half pitch.
And just for context, how small is that really?
Well, think about it like this. A single human hair is about 100,000 nanometers thick. We are trying to reliably pattern lines thousands of times smaller than that.
That context helps a lot. And the problem is that the established workhorse of the industry, this conventional 193 nanometer optical lithography, it's just hit its physical wall.
It really has. It simply cannot resolve features that tiny anymore.
So what's next?
Well, the industry spent billions developing new solutions. On one side, you have these high-resolution, bleeding-edge technologies like EUV extreme ultraviolet and electron beam lithography, or EBL.
Okay, they have the precision.
They do, but they are often still slow or just incredibly expensive to deploy at volume.
And then on the other side, you have the, let's say, clever optimization approach, which is multiple patterning lithography, MPL.
Precisely. MPL, like double patterning or triple patterning, it uses multiple exposures to enhance the capacity of the older optical systems.
So you're basically painting the picture in 2 or 3 steps instead of 1.
Exactly. It boosts throughput, but, it's not magic.
And that brings us to the core conflict here. Even after you split the design onto multiple masks, these complex layouts still have what the industry calls unresolvable conflicts. What does that mean in simple terms?
It means that certain pairs of features are simply too close together to be cleanly separated onto the different masks. If you try to draw both with your optical masks, they just blur together. They fail. It's an intrinsic conflict.
So if conventional tools, even with MPL, can't do it all, and the new tools like EBL are too slow to do it all, the solution has to be a marriage of the two.
It has to be, and our deep dive today is focused entirely on that. Hybrid lithography.
We're looking at research that details a new approach called the Layout Decomposition Co-optimization Framework.
Exactly. It combines the high throughput of MPL for the bulk of the design with the pinpoint precision of EBL to handle just those difficult, unresolvable conflicts.
And the mission here is key. This isn't just about solving conflicts, it's about solving them smartly. It's a simultaneous optimization.
That's the perfect word for it. We need to minimize manufacturing cost, which means minimizing stitches or cuts in the design while aggressively maximizing EBL throughput. And that just means using it as little as possible.
It's a classic high-stakes trade-off. Let's dive into that EBL bottleneck because that seems like the most expensive part of this whole workflow.
It is. So the hybrid process works in 2 stages. Most of the layout gets patterned fast and cheap by MPL.
And then you bring in the specialist.
Right. Only the critical, tightly spaced features, those unresolvable conflicts, are then manufactured using the high-resolution EBL system.
And because EBL is the limiting factor, every millisecond counts. We learned that the total writing time, which they call PEEL, has 3 parts. There's Taylor exposure time, which is the useful work.
And then there's Taylor-Baller's stage movement time and Taylor's stage settling time.
Okay, and the sources highlight this really critical, non-intuitive fact. Teelishly, the settling time is often the dominant time sink.
It completely dwarfs the useful exposure time.
Wait, settling time sounds like a purely mechanical pause. Why is that specific pause so much longer than the time spent actually moving the stage? Is the stage physically, wobbling for half a second?
It's more than just a simple wobble, though that is a factor. When the stage moves to a new subfield, a little section of the chip, the system has to physically stop. Then the mechanical vibration needs to dissipate, and the electron optics have to electronically stabilize and lock onto the new coordinates. That whole stabilization process, Teelers, is just fundamental overhead.
Okay, let's nail this home with that staggering data point from the source material. In one of the complex test cases, S38417, when they had to use these tiny subfields, the actual feature exposure time take tool was only 72 milliseconds.
Right. But the stage settling time, TUTALs, for all those required stops, was nearly 550 milliseconds.
550.
Yeah.
So that pause time was over 7 times the length of the useful work time.
It's a total throughput killer.
That's amazing. So the real goal isn't just reducing the amount of material EBL has to write. It's about reducing the number of times it has to start and stop.
Exactly. And the researchers proved this. By maximizing the subfield size in that same example, they could cluster the EBL work and eliminate the stops. The result was a stunning 88.5% reduction in total writing time.
Wow. Okay, so that fundamentally changes the optimization strategy. We aren't just counting conflicts anymore.
We're not. The most accurate throughput metric isn't the raw count of features written by the e-beam. The strategy shifted to minimizing the total area of the features written by EBL, because if you minimize the area, you can group the work into fewer, larger subfields and attack that debilitating settling time.
So the physical goal is clear. Cluster the EBL work, minimize the stops. But to do that, you need a mathematical model. How do they translate this hardware challenge into graph theory?
This is where the real innovation lies. Historically, people used a sequential or two-stage approach. They would decide where to put the stitches first, and then they try to minimize EBL usage.
But that seems suboptimal. The decisions you make in stage 1 are going to hamstring you in stage 2.
Precisely. To achieve true co-optimization, they had to merge these two conflicting goals, EBL area and stitch cost, into a single unified mathematical problem. They formulated it as a minimum vertex deletion K partition problem.
Okay, let's break that down. K is just the number of masks in the MPL process. So for double patterning, K is 2.
Right, and you're just trying to color the layout graph with two colors, making sure no two conflicting features share the same color. That's called minimum vertex deletion bipartization, or MVDB. It's still hard, but much more solvable.
And if K is 3 for triple patterning, I imagine the complexity just explodes.
It really does. So they defined the objective function to minimize this weighted sum of EBL area and stitch cost. You have the EBL cost, alpha, and the stitch cost, beta.
And in the real world, the cost of running that EBL machine is just vastly higher.
Oh, much, much higher. So the weight factor alpha is set way higher than beta. This tells the mathematical solver to always try to avoid EBL first. It will only insert a stitch if that stitch prevents an even more expensive use of EBL.
But this is where I get lost in the abstraction. The core problem is solved by deleting vertices, assigning a feature to EBL. How do you include the concept of a stitch, which is like a cut or an edge in the graph, into a vertex deletion problem?
It's the most elegant part of the whole framework. They introduce a virtual node. Every potential stitch location in the conflict graph is represented by one of these virtual nodes, connected by two virtual edges.
Help me visualize this. Is it like putting a cost-labeled placeholder into the design that represents the option of making a stitch?
That's a perfect way to think of it. If the optimization determines that the two features connected by that virtual node can be separated onto different masks without any issue, it just retains the virtual node. The stitch is unused.
And what happens when a conflict arises? An odd cycle that has to be broken.
If the conflict forces the algorithm to break the cycle by deleting that virtual node, that deletion is equivalent to inserting the stitch into the design. And because the virtual node is assigned the stitch cost, beta, the entire process is unified.
So whether the system deletes a feature and pays the high-cost alpha, or deletes a virtual node and pays the low-cost beta, it's all just one big vertex deletion problem.
It's a single-weighted mechanism to find the cheapest overall solution.
That's genuinely brilliant. By making the stitch a vertex, they can solve both problems at the same time, not one after the other.
Absolutely. And that unification is the core reason for the performance gains we're about to see.
Okay, so since most of the industry uses DPL, let's focus on that K=2 case, the minimum vertex deletion bipartization problem. They use something called primal dual, or PD, methods to solve this.
The primal dual approach is a standard way to find near optimal solutions to these hard problems, but to do it quickly. They developed two versions, starting with a planar PD method. This method assumed the conflict graph was nearly planar, not too tangled, but it required some intense computational overhead.
Right, I remember reading that. It had some really specific steps.
It did. It had to find a maximum planar subgraph, then it had to identify and remove what they called non-cyclable edges, things like dangling edges or bridge edges that don't actually form a conflict cycle.
This sounds incredibly slow. If you're trying to speed up manufacturing, adding that much mathematical complexity seems, well, counterproductive.
It was, which is why the alternative was the non-planar PD method. This one was simpler, more general, and it just skipped that entire planarization process. Instead, it used a rapid depth-first search, or DFS, to find an odd cycle, a conflict.
Okay, so once it finds a conflict cycle, how does it decide which vertex is the best one to sacrifice to the e-beam?
It identifies what it calls the most tight node. In simple terms, it finds the node within that conflict cycle that has the lowest gap weight. That means it's the cheapest available feature to assign to EBL. It removes that node, pays the cost, and just repeats the process until the layout is perfectly bipartite.
So it's a greedy algorithm. It just keeps finding the cheapest conflict point, deleting it, and moving on until the layout is clean.
Exactly. It's a very calculated, greedy approach based on those weights we talked about.
Now, what about the more complex systems, k greater than 2, like triple patterning? The PD method doesn't really extend to that, so what do?
They needed a wrapper. They developed something called RILS, Random Initialized Iterative Improvement Local Search. You can think of RILS as an intelligent brute force organizer. It just initializes the layout randomly and then iteratively applies that really fast PD solver to multiple two-mask subsets of the larger layout.
So RLS doesn't solve TPL directly. It breaks the TPL problem down into a bunch of smaller, manageable DPL problems and keeps refining until it finds the best solution it can.
Precisely. It's a pragmatic way to leverage the efficiency of the k=2 solver for these much harder problems.
Okay, let's get to the payoff. Did all this mathematical rigor translate into actual savings? What were the headline numbers?
The results were definitive. For DPL plus EBL, the PD co-optimization methods reduced the total required EBL area by an average of 65.5%.
65%. That is not a small optimization. That's a complete transformation of the throughput.
And critically, they simultaneously reduced the number of costly stitches by 69.2% on average. So co-optimization wasn't just solving one problem, it was achieving these huge reductions in both expensive variables.
And for the more complex TPL case with RLS.
Still very impressive. Using RLS with the PD solver, they still reduced the total EBL area by 38.7% on average, so the concept scales.
And here's the kicker for me. What about those two algorithms? All that heavy lifting for the planar PD method, did it actually pay off?
No. Shockingly, the non-planar PD method, the simpler one, it provided similar or even slightly better results while running significantly faster.
So for real-world implementation, simplicity and speed win.
They often do. It's a huge lesson for designers.
This all culminates in the powerful control the framework gives the chip designer. Let's just revisit those weight factors, alpha and beta. This framework really lets you tune the economics of the chip.
It absolutely does. The weights let you fine-tune that trade-off. If a designer sets the stitch weight, beta very small, say 0.01, the system prioritizes minimizing that extremely high-cost EBL usage, even if it has to add more stitches.
So high throughput, but maybe a more complex layout. What if the designer is worried about physical robustness and wants to minimize stitches?
They just raise the stitch weight dramatically, maybe to 100. And this forces the solution to avoid stitches almost entirely, but there's a clear price tag attached. Avoiding those stitches forces the EBL area to increase by 21% on average to resolve the conflicts that stitches would have cheaply absorbed.
That 21% is the real-world premium you pay for a physically cleaner layout. That precise control over the throughput versus complexity trade-off is, I think, the biggest takeaway here.
I agree. The simultaneous co-optimization framework is a massive leap forward. By marrying the mathematical modeling with the physical constraints of lithography, they achieved huge quantifiable reductions.
So what does this all mean for the future? If the software optimization is this powerful, what's the next frontier?
That's the provocative question, isn't it?
Hmm.
While algorithms like these can dramatically reduce which features need EBL, the ultimate limit on throughput is still purely physical. We saw those huge gains from maximizing the subfield size to kill that settling time. The problem is, you can only push that so far. The EBL system itself imposes hard physical constraints limits on pattern resolution, the capabilities of the digital to analog converter hardware that restrict how big that subfield can be. So the next big challenge isn't just better software, but pushing those underlying physical hardware limitations to squeeze even more speed out of the E-beam process itself.